So I've made up some fresh solvent and I've spotted some fresh plates. So you can see that I've got some nice spots on each of those plates. And I've made up a mixture for vanillin that's 2 parts pet ether to 1 part ethyl acetate, 2-to-1 mixture, made up 3 milliliters. And for the cinnamic acid, I made up a 1-to-1 mixture, but without the triethylamine. So equal amounts petroleum ether and ethyl acetate. Hopefully that'll get those spots to move pretty well. And then for the tryptamine, I've gone ahead and made up a mixture of methanol, 1 part methanol to 9 parts methylene chloride or dichloromethane, and again added 5 drops of triethylamine. So a 1 to 9 or 10% methanol in methylene chloride mixture works for a lot of amines. I'm hoping it will work for tryptamine. And the triethylamine in there, again, is necessary to prevent these amine from getting protonated by the acidic silica gel and therefore becoming a salt, because salt will have an RF of 0. They just won't move at all. So while we're waiting for those plates to develop, I want to show you that if the compounds do not absorb UV light, for instance, because they don't have any significant pi bonds in them, one way to allow the spots to show up is to use iodine, I2. So we have crystalline iodine here suspended in a matrix of sand, and iodine will stain a lot of different compounds by reacting with double bonds. So I'm not sure which of these compounds will stain with iodine, but the process is very simple. You just kind of allow the plates to be submerged in the iodine impregnated silica, and you let them sit, and you can get dark brown spots on a light brown background. The silica gel and the fluorescent indicator won't absorb iodine to any appreciable extent, but certainly if there are pi bonds in there, like there is in cinnamic acid, we have that trans double bond in there, or often if there are aldehydes or hydroxyl groups, vanillin has both of those. Sometimes when you have NH2 groups, amines, they'll also stain with iodine. So all 3 of these compounds have functional groups that may stain with iodine, and that's a good way to visualize spots. Even if you don't have that extended pi system, you can see your spots by staining them. There are a bunch of different possible stains. Iodine is just one. In the TLC lab later, we'll be using phosphomolybdic acid, which often stains oxidizable functional groups like double bonds and aldehydes and things like that, and gives blue spots on a pale green background. Vanillin itself can be used as a TLC stain. It will react with a lot of different things to form brown spots. So we just let that sit in there for a little while. Unfortunately, triethylamine, because it's an amine, tends to stain with iodine, so if you've had your plate developed in a solvent system that contains triethylamine, it's often a little bit messy. Now, and I'm going to use tweezers to take those out. And we'll give this a look and see if that's developed. No, it's still got a little ways to go. So we can take these plates out and see what things look like with iodine stain. So you can see that the vanillin stained very nicely with iodine, but it appears that the cinnamic acid really didn't, at least not very strongly. So that's actually also a way of distinguishing them. So in this case we've got nice dark spots for the vanillin. Clearly that lower spot that didn't stain with the iodine is something else. Looks like we've got a little bit of spot at the baseline that's impure too, but that's not cinnamic acid. If we look at the cinnamic acid, we can see clearly that the extract and the co-spot have a spot that's staining with iodine, whereas the standard really isn't. So that's an indication that there's vanillin in the cinnamic acid. And you can see that triethylamine is causing the whole plate to go pretty dark, which means it's a little difficult to tell whether the tryptamine is actually staining or not. We can let that sit. The iodine will gradually evaporate off the plate, and it may be that those spots will become visible over time. So that's a good solvent front for the vanillin. And the other two need to go a little bit longer. So we can take a look under UV light here, and we can see that that's a little better. We've moved that vanillin up the plate more. So a 2-to-1 mixture, 2 parts petroleum ether to 1 part ethyl acetate seems to work better. We definitely have contamination with cinnamic acid though, which is highly UV active. And that's consistent with what we saw in the GC mass spec as well. And we can stain that with iodine. We know the vanillin stains nicely. Here's our cinnamic acid. This was developed in the 1-to-1 mixture. So you see that the standard is spotted on there probably a little too heavily. It looks like there's a little bit of vanillin at a higher spot, but the cinnamic acid looks like it's at least mostly cinnamic acid with only a fairly small amount of vanillin. And then you can see if the tryptamine moved at all. And that solvent front moved up to about halfway through the writing. And you can see that the tryptamine does move in this 1-to-9 methanol dichloromethane. It streaks a little bit. The triethylamine will reduce that streaking, and it looks like there are some slightly higher RF spots, some small impurities in the tryptamine, which is consistent with the fact that it's quite colored. The other thing you'll notice about the tryptamine is that it's not just a dark background, it actually is kind of glowing a little bit. Tryptamine itself appears to be fluorescent, so it's absorbing the UV light and then giving us back a brighter yellow, or a brighter purple, I mean, absorbing the yellow. And you can see the difference if you look at them side by side between these spots that are simply kind of a darker color and these spots which are glowing purple. At least maybe you can see that difference. I can see that difference. Put them side by side a little bit more, right? Just kind of a dark spot versus a brighter purple spot. So tryptamine itself appears to be fluorescent, which is an interesting feature. So the tryptamine's pretty clean, nice across, right? Our standard, our co-spot, and our extract look very similar. These spots are tiny, and there's a little bit of it even in the starting tryptamine, the commercial sample, which is consistent with the fact that the commercial sample is in fact not white. Here's our vanillin, and we see that we got a nice dark spot staining with the iodine and the cinnamic acid impurity. And I'm not going to bother staining the other two because we know, well, that the cinnamic acid doesn't stain, and we really don't need it for the tryptamine. It's hard to tell. I wouldn't expect the tryptamine to be staining because the aromatic system doesn't usually stain, and the amine itself probably isn't staining with iodine. So I'll take a picture of these and I will upload these, and you can measure the RF. For the nice tight spots like here in vanillin, the center of the spot is the thing to use. For the cinnamic acid, you can kind of choose to either use the center of the spot, or sometimes people use the leading edge of the spot, but that's streaked a little bit. For the tryptamine, again, the center of the spot or the leading edge of the spot, just as long as you're consistent. So much better TLC results For cinnamic acid, a 1-to-1 mixture of ethyl acetate and petroleum ether seemed to work pretty well. For vanillin, a 1-to-2 mixture, 1 ethyl acetate to 2 petroleum ether. It's a pretty good system. We could even run it in 1-to-1 and it would work well. And then for the tryptamine, a 1-to-9 mixture of methanol and dichloromethane worked. We could even go a little bit more polar and perhaps do a 2-to-8 mixture of methanol and dichloromethane if we wanted to get those spots a little further up, closer to the solvent front.